Welcome back, everyone. So let me fix that so it doesn't look like my cranium has been cut off. I keep making that mistake. Anyway, let's continue on and finish chapter 9 with just one section, 9.7, which is the section on the formation of hemiacetals and acetals from aldehydes and ketones. And trust me, this section is a mouthful. I think it's more than fine to have just one video just on this section. This is also a re-upload of the one from before that had no audio, so hopefully we don't get that same gremlin this time. I certainly will double check before uploading. In any case, we've looked at a variety of different nucleophiles attacking that all-important electrophilic carbonyl carbon. We saw how the cyanide ion can do that, to give us cyanohydrins. We saw how water can do that in an otherwise synthetically useless hydration reaction. And all we need to do is change one of the hydrogen atoms on water to an alkyl group, and we've got ourselves an alcohol. And indeed, alcohols can also add to aldehydes and ketones in the presence of an acid catalyst. And indeed, this reaction does not work under alkaline conditions, only under acidic conditions. And the reason for that is that if you tried to do this reaction under alkaline conditions, you would wind up with an intermediate that just has O- here that then could not react any further. It would then fall apart and go back to the starting materials. So this reaction requires acidic pH, also generally requires heat. Sometimes the problem will mention heat, sometimes it will not. You know that OWL is sometimes, whether purposely or not, somewhat sloppy. But I do believe in real life these generally need to be heated. The reaction tends to be somewhat endothermic. And the idea is when you add a little bit of acid, which by the way, this acid, they might write H+, they might write H2SO4, or some other strong acid. It doesn't really matter what the identity of the strong acid is. What matters is that we add just a little bit of the acid, just a catalytic amount, and when all of that acid dissolves in the alcohol solvent, then some of those alcohol molecules will get protonated, and you will wind up getting a little bit of the conjugate acid of the alcohol, and that's going to act as our proton donor. And indeed, the first step of this reaction, just like the first step of hydration under acidic conditions, involves protonating that carbonyl oxygen. And I think you'll find that's a common theme in reactions of carbonyl compounds in acidic medium. In general, we need to protonate that oxygen first if we're in an acidic medium. That does two things. First of all, it makes the already electrophilic carbonyl carbon even more electrophilic, because now it's attached to an oxygen with a full +1 charge on it. The other thing it does is it makes it so that after nucleophilic attack, we wind up getting a neutrally charged oxygen or an uncharged oxygen. If we didn't protonate that first, then instead of OH, we'd have O- here. And that's a big no-no in acidic solution. Remember, in acidic solution, we want to avoid having any strongly alkaline species. So no OH-, no alkoxide ions, which that would be, right? No NH2- or carban ions, certainly, nothing like that. Those don't belong in acidic medium. Anyway, after protonating our carbonyl oxygen, we wind up with the protonated species, as you see here, and now a molecule of methanol can attack, and that's what's going to happen next. Notice that I'm not showing an ion CH3O- attacking, so you will get this species that you see here with that oxygen from the methanol still protonated. The reason we can't use CH3O- is, again, we're in acidic medium. And a species like that cannot exist in acidic medium. It's much too strongly basic. And we know that from the pKa's of alcohols, which aliphatic alcohols tend to be round and about in the upper teens, maybe 18, maybe 19, somewhere in there. And if we're at an acidic pH, let's say we're at pH 1 or 2, there is no way you're going to get any deprotonation of the alcohol to form the alkoxide ion. Not an acidic medium. Alkaline medium, maybe. Then we could maybe contemplate intermediates like that, but never an acidic medium. Certainly not in any reasonable concentration. So far so good. By the way, I'll just mention that I'm not even showing the curved arrows here. And this is something that just came to my mind as I was thinking about how to teach this course, which I'm still very much making up as I go along. I don't mind showing you curved arrows and making you responsible for curved arrow mechanisms if it's a relatively short reaction, 2 or maybe at most 3 steps. When you've got 7 steps like here, that's a bit much, and I really don't want to burden you. Now, the flip side of that is understanding the mechanism with curved arrows also increases your understanding of the reaction itself. But for my money, if I can just help you guys to understand what the different intermediates are, to understand that we really do need to show every single one of those intermediates, right? All of those have been experimentally determined to be there since decades ago. As long as we can do that for these longer reactions, I'm really fine if you don't learn all of the curved arrow notation. If you want to, that would certainly make me very happy. As I'm fond of saying, that will warm my tiny, stony, cold, black, dead, dark organic chemist's heart. But if you simply understand the flow of the reaction in terms of what the intermediates are that are formed, I think that's more than enough level of understanding for us. So here we have our initial adduct with of the methanol to the carbonyl group. Now what we need to do is some proton transfers in order to make sure that we can lose a molecule of water. And so first of all, what we need to do is pull off this proton from this positively charged oxygen, and so doing gets rid of the plus charge in the oxygen. And for those curious, it's actually a methanol molecule that's going to do that for us. Remember, everything's swimming in an ocean of methanol. Methanol is our solvent here. And I'm only using methanol as an example, and I'm only using, indeed, cyclohexanone as an example. I could have used any other aldehyde or ketone, and any other reasonably small alcohol would work just fine. So a methanol molecule will pull that proton off for us, and we get our neutral hemiacetal. But in general, we're not going to stop at the hemiacetal. This is going to continue to react. The only times we'll wind up staying at the hemiacetal phase are when this hemiacetal is cyclic. And we're going to see that happening in chapter 16 when we start talking about sugars. That's going to be coming up real soon, perhaps even later tonight as I'm speaking, from my perspective, because I want to get us started on that. Good, so this species is our hemiacetal. The definition of the hemiacetal is a species that has an sp3 hybridized carbon with OH and O-alkyl directly attached to it. That's what we mean by a hemiacetal. This is actually going to react further. Now what will happen is a proton will get transferred again from the conjugate acid of our solvent to the OH oxygen, and we'll get this species here. Now, we also cover this reaction in Chemistry 228, though in a good deal more depth. But I'm thinking of some common questions that I get there, and I'm confident you guys will have very similar questions. 2 questions that generally occur here. One of them is, does it matter if we pull this proton off first and add that proton second, or can we reverse the order? I'm sure a lot of you are wondering that. It's a great question. And the answer is we do have to do things in this order. The reason is if we didn't pull off this proton first, but went ahead and protonated that oxygen here first, then we would wind up with an intermediate with a +2 charge. And that's very unfavorable. We want to avoid that at all costs. We want to make sure that the intermediates we draw are going to have a total charge of either +1, -1, or 0. And I can't even really think of an exception to that. At least I'm pretty confident we're never going to run into one. So that's why we pull off this proton first to go to a neutral intermediate and then protonate to go back to another species with a +1 charge. The other thing that a lot of sharp-eyed students, probably a lot of you too, will notice is, why don't we just take this oxygen and use it to pull that proton off and skip a step and go straight here? It's, again, a very reasonable and understandable question. And the reason why that doesn't happen can be answered on a couple different levels. One way I could answer that question is on the cynical level and just say, because that's wrong, which is very true, but doesn't really help you at all. But a much better answer, and I think a much more helpful answer, is the reason that that can't happen is because that would require a 4-membered transition state. And what I mean by that is, if you count from this oxygen over to the proton you propose putting onto it, you'll count from 1 to 4. 1, 2, 3, 4. And that means that the oxygen and all the intervening 2 carbon and oxygen atoms, and then that hydrogen on the end, need to bend around into a 4-membered ring in order for that to happen. And if you recall, when we first started talking about cyclic compounds, we said 3- and 4-membered rings are very strained. And that's the same thing here. It's just too far away. It would have to form an extremely strained 4-membered transition state in order to make that intramolecular proton transfer possible. And so that's not something that we can count on happening, not with a 4-member transition state. 5- or 6-member transition states, yes, those are going to be fine, because as you recall, 5- and 6-membered rings are a good deal less strained. 6-membered rings essentially perfectly unstrained, and 5-membered rings darn close, darn close. So 4-member transition states, 3-member transition states certainly are essentially right out. I can't say they never occur, but only in extraordinary circumstances. And certainly these circumstances are far from extraordinary. So that's why we do this in 2 steps, and those 2 steps in that order. Anyway, once we formed this protonated species, now we've got a water molecule that can act as the leaving group. If we hadn't protonated that oxygen first, then we would be trying to lose OH- as a leaving group, which would never, ever happen in acidic medium. Again, the hydroxide ion, you know, is a very powerful base. And so we're not going to be able to lose the hydroxide ion as a leaving group. Not in acidic solution. In alkaline solution, yes, maybe something like that could happen, but not in acidic solution. So that's why we protonate that first. These things are what will help you remember the story of how we get from this molecule to this one in the several steps that it takes. So once we lose the water molecule, we get an intermediate that looks like this. And the thing I'd like you to notice about this intermediate is it looks an awful lot like that one that we had before. In fact, all we've done is replaced a hydrogen with a methyl group. So we would expect it to have the same type of reactivity, to once more be prone to nucleophilic attack from a methanol molecule, which again, we have plenty of. Methanol is the solvent. There's probably some thousands or tens of thousands of mole equivalents of methanol present. And so that attacks once again. We form an intermediate that looks like this, and now a methanol molecule comes along, pulls off that proton, and gives us our final stable neutral acetal product. So that's the scheme, that's the mechanism that these all follow. And this is going to become very important in the next chapter, because hemiacetals and hemiacetals and full acetals become important in the reactions of sugar molecules. And it also occurs to me way back in chapter 18, I think it is, when we talked about nucleic acids, we talked about an NO acetal. And that's just like a regular acetal, except that instead of 2 oxygens attached, or 2 alkoxy groups attached to an sp3 hybridized carbon, one of those 2 alkoxy groups is replaced with an amino nitrogen atom. But it's the same type of molecule. And you may recall that we called that back then an NO acetal. So this is a regular acetal, meaning it is an sp3 hybridized carbon attached to 2 alkoxy groups. And so that's that reaction. Now, as I pointed out, when we get into carbohydrates coming up very soon, we'll learn that you can get cyclic hemiacetals. Generally, these are going to be of 5 or 6 membered rings. And so the chapter gives you, I would say, a good model system for that, using a molecule that they correctly name 5-hydroxypentanal. So I'll leave that for you to read about on your own. I think the textbook's treatment of that idea is very good, and it'll again get you ready to think of the sorts of structural features that we'll be talking about in chapter 16. The only other point I want to make is that you can make a cyclic acetal by using a diol of the right length. So if instead of using methanol, what if we used ethylene glycol, which is 1,2-ethane diol? Well, in that case, you can have both of the OH groups in the same molecule wind up one after the other attacking that carbonyl carbon, and thus you will form a ring. And especially in cases where you can get a 5 or 6 membered ring, in this case we'll get a 5 membered ring, those are the times that you can count on forming a nice stable cyclic acetal. The mechanism, though, is identical. So if we were to dissolve, let's say, 3-pentanone, again, I could have picked any aldehyde or ketone, but let's just say we used 3-pentanone and heated that up in ethylene glycol with an acid catalyst. Again, you would get a little bit of the conjugate acid of ethylene glycol. It will protonate just one of those oxygens. Chances of both oxygens being protonated, first of all, just in terms of probability, is nil. And second of all, again, you'd get an intermediate with a +2 charge. So that species is a non-factor. Anyway, once we've protonated that oxygen, just as we did before, a molecule of ethylene glycol can attack, and that will look like this. And now, once again, we need to take 2 steps. First, deprotonating this oxygen with a plus charge to go to our hemiacetal form, and then protonating the OH oxygen so that we can now prepare the molecule to lose a molecule of water, which reminds me of something I neglected to mention a moment ago. That water molecule is now effectively removed from solution. What do I mean by that? By that I mean that we're forming 1 mole equivalent of water that now is drowning in this ocean of our alcohol, whether it's ethylene glycol or methanol. And it's diluted so much that it's a non-factor now. It's not going to play any further role in the mechanism. So that means that after we lose a water molecule, this reaction is no longer reversible. Up until now, we could imagine the steps going backwards and reforming the starting material. But once we lose the water molecule, we're committed. It's going to go on. So again, we lose a molecule of water. And now, rather than another molecule of ethylene glycol coming in, instead we have this nicely, readily available OH group in the same molecule. And in general, intramolecular reactions, meaning those that occur within the same molecule, are greatly favored over intermolecular reactions, those that occur between multiple molecules, most especially when, like in this case, we can form a new 5 or 6 membered ring by forming a new bond. And that's exactly what happens here. So this OH group will attack our carbonyl carbon. We get this protonated acetal. And then again, an alcohol molecule comes along and pulls off that proton, and we get our final acetal. So do take a look at these, practice these mechanisms. And if you have any further questions about the various intermediates or why the steps occur as they do, please feel free to stop by. I'm available during my office hours. Other than that, have a good day, and we'll see you next time.